All right, welcome everyone. In this lesson, we're going to see how to estimate the value of our derivative given either the graph of our function or a table of function values. And this is going to allow us to investigate the derivative in a few more kind of different applications. So we'll be able to interpret what the derivative means in those applications. And it's also going to be helpful to consider the units. So what are the units for our derivative? All right, so let's start with just a little bit of new terminology. So these are gadgets we've been working with. We've been working with difference quotients and then the limit of those difference quotients. And let's give these kind of a more general name. So we've looked at them really in the context of tangent lines and velocity. But for a general function f, what does the difference quotient represent? Well, we're going to call that the average rate of change of our function over the interval from a to b. So this difference quotient, f of b minus f of a over b minus a, we're going to call that our average rate of change over that interval ab. And so we've looked at this, like I said, in the tangent problem and then in our velocity problem. So how do we find the slope of the tangent line? How do we find the instantaneous velocity of an object moving in a straight line? Those were the two main kind of examples that we started with that led us down the derivative rabbit hole, I guess. So tangent. For the problem of a tangent line, what does our function f represent? Well, you can think of f as representing the height. So we have a curve, and the function values actually represent the height of that curve above the x-axis. And in the context of that height function, what did this difference quotient represent? Well, the difference quotient represented the slope of the secant line connecting 2 points on the curve. Okay. And then what did we see when we actually calculated the limit of that difference quotient? Well, that actually gave us the slope of the tangent line. All right, for velocity, what were we working with for the velocity problem? Well, here we had a position function, which we normally call s of t. So this describes the position of our object moving at time t. And so what did the difference quotient represent? What did just the difference quotient represent in that case? Well, similar language. It was the average velocity over that specific time interval. And so when we actually did the limit of that difference quotient, what did we get? Well, we actually got the instantaneous velocity at time t equals a. So for the tangent line problem, this difference quotient represented the slope of the secant line connecting points P and Q. And for the velocity problem, it was the average velocity during a specific time interval. Now let's just So that's what our difference quotient represents in each of those cases. Now for our instantaneous rate of change, when we do the limit as b approaches a, for the tangent problem, we get the slope of the secant line, and for the velocity problem, we get the instantaneous velocity. And so we're just kind of introducing this language of saying, all right, we have this difference quotient f of b minus f of a divided by b minus a. For just a general function, we call that the average velocity of function f over that time interval ab. If we do the limit as b approaches a of that difference quotient, well, then we get the instantaneous rate of change of our function directly at a. All right, so there is one other slightly different version of this formula that we've looked at, and it is the limit as h goes to 0 of f of a plus h minus f of a, all divided by h. And so the idea here between the average rate of change and the instantaneous rate of change is we're really shrinking down this interval. So the instantaneous rate of change really shrinks the interval AB. We're going to shrink that down so we get closer and closer to A. So we're going to shrink this interval down, this interval AB down, and we're going to shrink it down to the one endpoint at A. And doing that, doing the limit as we shrink that interval, is giving us the instantaneous rate of change directly at A. Now, to kind of see where the conversion happens, h here represents the length of the interval. So we let h represent the length of the interval. And so if b is approaching a, that means h has to be approaching 0. So the actual size, the actual length of our interval there has to be approaching 0. So the conversion is, we generally say h is equal to b minus a. So that's the length. That's how you calculate the length of an interval. Subtract the endpoints. And so when we look at our formula here, b minus a, we replace that with h. You can solve the b here, solve for b, and you get a plus h. And if b is approaching a, like we are in this limit, this version, then if b is approaching a, that means the length of our interval has to be getting closer and closer to 0. Those two endpoints are getting closer and closer, so this difference is going to 0. So you can see how the conversion process works. And we've looked at this before. So there's two different versions here. A lot of times we use this version. It's a little bit easier to work with, but this version's also perfectly fine. All right, so that's just some of the terminology we're going to be looking at in this lesson.